Hello everyone, welcome back to my channel For the Love of Physics. I am 𝓬𝏬𝏬𝏬𝏬𝏬𝏬𝏬𝏬𝏬𝏬𝏬 and today we are discussing pair production and pair annihilation. In my last couple of lectures, we talked about various phenomena that we see when radiation interacts with matter. For example, black body radiation, photoelectric effect, Compton effect, etc. To complete that discussion, today we have something called pair production. So when extremely high energetic radiation interacts with matter, in that situation, we end up seeing something called pair production. Pair production is a very unique, very interesting phenomena because you end up seeing the conversion of electromagnetic energy into matter energy. So electromagnetic energy in the form of a light photon gets converted into matter particles in the form of electrons or positrons, etc. And therefore, this provides a very concrete proof for two very interesting things. First, it provides a concrete proof to the very famous equation E equals mc square in relativity, where energy and mass are interconvertible. Mass and energy can be converted to each other. So it provides a concrete proof of that. It also provides a concrete proof of what we call relativistic quantum mechanics. So later on, we are going to see that there is something called relativistic quantum mechanics for particles which are microscopic and also traveling at very, very high velocities near about the speed of light, which was provided by Paul Dirac. So Dirac's relativistic quantum mechanics predicts the existence of negative energy particles, also known as antiparticles. And later on in 1932, when a scientist by the name of Anderson was studying the trails left by cosmic rays in cloud chambers, he was able to successfully prove the existence of these antiparticles that was predicted by relativistic quantum mechanics. And also, it is very important as a discussion for us because this is one of those experiments in which a light photon demonstrates conservation of energy, conservation of momentum when it gets converted into matter particles. So pair production is something that happens whenever radiation interacts with matter, but that radiation must have a very high amount of energy. So if a radiation has a low energy, you may end up seeing something called photoelectric effect. If the radiation has a little bit greater energy, you may end up seeing something like Compton effect. If the radiation has extremely high energy as it interacts with a matter particle, then you end up seeing something called pair production. So for example, if you have some kind of a radiation, and I'm going to draw this wave, okay, just to signify that we are talking about a photon particle. Photon particles are classically thought of as waves, even though we have demonstrated in my past lectures that they behave as particles in certain circumstances. But to differentiate a photon from an electron or a positron diagrammatically, we are using this kind of a wave as it comes and approaches, let's suppose, a nucleus. All right, so let's suppose that we have a nucleus which is bombarded with extremely high energetic radiation. So this hν is extremely high, of the order of few mega electron volts. And then we end up seeing something that is very unique, that this radiation vanishes and we end up creating a pair of particles. So one example, so this is just one of the many examples that exists in nature. All right. So one example is the existence of or the creation of an electron and a positron. Now the question may be, what is a positron? You see, positron is the antiparticle version of an electron. So you are already familiar with what electrons are, right? Electrons are subatomic particles. These are fundamental particles. And corresponding to electrons, you have positrons. Positrons are the antiparticle of electrons. And if you look at the properties of a positron, the positron has exactly the same mass as that of an electron. It has exactly the same magnitude of charge, but the sign of the charge is different. So the electron may be negatively charged, but the positron is positively charged. And it also has opposite magnetic moment. Now, why is it called an antiparticle? It is called an antiparticle because when a particle and an antiparticle come together, then they annihilate each other, they destroy each other, both of them vanish, and all that remains is pure energy. So whenever an antiparticle, any antiparticle meets its particle version, they annihilate and create pure energy. But this, what is happening here, is the opposite. Pure energy in the form of a photon in the presence of a nucleus becomes or ends up creating a pair of an electron and a positron. This is a very interesting and very unique phenomena, and it is not possible without satisfying various conservation laws. So if you look at the concept of pair production, it must satisfy various conservation laws. So first of all, it must satisfy the conservation of charge. So if you look at a photon does not have a charge. So the net charge of an electron and a positron is also zero, just like a photon. Yes, electron is negatively charged, positron is positively charged. So the net charge of electron, positron is zero, net charge of a photon is zero. That means charge is conserved. The second important conservation law that it follows is the conservation of energy. So you see, the pair production phenomena is a very good example of how energy is converted into matter. You see, the initial photon, it has what? It has energy of h-nu, right? And the moment it comes into presence of a nucleus, it has a tendency to end up creating a positron and an electron. Positron, electron, these are matter particles. They have mass, right? So this energy ends up converting to mass energy of the particles as well as kinetic energy of the particles. So if I write that the h-nu gets converted into, let's suppose, the total relativistic energy of an electron, E minus, and the total relativistic energy of the positron, E plus. So E minus consists of the total relativistic energy of the electron, which is essentially the rest mass energy plus additional kinetic energy. So the rest mass energy of an electron is m0 c square, and let's suppose it also has some kinetic energy, E k E minus. So this is the relativistic kinetic energy. Okay, so usually when we talk about particles that are traveling at very low velocities, we can say that its total energy is rest mass energy plus kinetic energy. But in a broader sense, what I mean is a relativistic kinetic energy, which is the amount of energy that is total energy minus the rest mass energy. Okay, and E plus, which is again because the mass of a positron is the same as that of an electron, it also has rest mass energy of m0 c square, and any kind of an additional kinetic energy or relativistic kinetic energy associated with the positron, because the moment they are created, they are moving, right? They have some motion, so they have a kinetic energy associated with it. So therefore, the total energy of the photon ends up into the rest mass energy of the electron and the positron plus the additional kinetic energies that they may possess. Now there is an additional energy term here, that is the recoil of the nucleus. You see, the presence of a nucleus is very important in pair production phenomena, because the nucleus acts as something that conserves linear momentum. It experiences a certain amount of recoil. In the absence of nucleus, we will never see pair production happening in the first place. So the nucleus experiences a recoil and thereby balances conservation of linear momentum, and therefore the nucleus also experiences some kind of kinetic energy. But because the nucleus has extremely high amount of mass compared to the electrons, the total amount of kinetic energy associated with the nucleus is extremely minute, and usually for all practical purposes it could be ignored. So we can say that approximately speaking, almost all the photon energy gets converted into this. That means if we require a photon to induce this kind of a phenomena, it must have minimum this much amount of energy, right? It must have minimum this much amount of energy. Now what is the value of this? This is the rest mass energy of the electron into 2. So if you look at the rest mass energy of an electron, m0 c square, the mass of an electron is 9.1 into 10 to the power minus 31 kg in SI units, but in terms of electron volt, the mass of an electron is 0.511 mega electron volt upon c square. So there are different ways of writing down the mass of a subatomic particle. So if you look at the mass of a subatomic particle like an electron, it is 9.1 into 10 to the power minus 31 kgs in SI units. But if you look at high energy physics, mostly because we are in the domain of particle physics, right? Many of the times the masses are not written in terms of kgs, but they are written in terms of energy. The reason is being energy and mass can be converted, right, in between one another. Therefore, amongst particle physicists, they usually refer to the mass in terms of energy units. So if I convert this in energy units, it comes out to be 0.511 mega electron volt upon c square. So this is m naught c square. So this comes out to be 0.511 mega electron volt, and twice m naught c square therefore comes out to be 2 times this, which is 1.02 mega electron volt. That means for any photon to be responsible for the phenomena of pair production, it must carry a minimum of this much energy, because this is required to create the particle-antiparticle pair in the first place, and any additional amount of energy will go into the kinetic energies of the particles, but this is the minimum amount of energy that is required. So if the photon has this much amount of energy, then what is the wavelength or the frequency associated with the photon? We can actually calculate and see. So what is the energy of a photon? The energy of a photon is given by h nu, right? So the energy of a photon is given by E is equal to h nu. What is nu? Nu is the frequency. So in terms of wavelength, if I write this, this comes out to be hc upon lambda. So what is lambda? Lambda is equal to hc upon E, right? So if I plug in all the values, h is a Planck's constant, which comes out to be 6.626 into 10 to the power minus 34 joule seconds times, this should be hc upon lambda, right? So nu is equal to hc upon E. So c is the speed of light, which is 3 into 10 to the power 8 meters per second, and this comes out to be in the denominator E, which is minimum amount is 1.02 mega electron volt. So 1.02 mega is 10 to the power 6. Electron volt is 1.6 into 10 to the power minus 19. Now if we calculate this and come up with a number, I have already calculated it here. The number comes out to be around 1.2 picometers. So 1.2 into 10 to the power minus 12 meters, or 1.2 picometers. This is the minimum amount of or the maximum amount of wavelength that the photon should have to be able to induce this kind of a particle-antiparticle creation. Now usually the light that we see around us in our day-to-day life is a visible light. The visible light has a wavelength of the order of around 4,000, 5,000 angstroms, right? Picometers is extremely small compared to an angstrom. An angstrom is 10 to the minus 10 meters. So 4,000, 5,000 angstrom is around a few micrometers, right? So picometers actually falls in the range of gamma photons. So gamma radiation. So these are extremely high energetic, low wavelength, high frequency photons, which are gamma radiation. So only exceptionally high energetic gamma photons are capable even of inducing these kind of pair production phenomena. Now, coming to the presence of a nucleus, I said that it is impossible for this kind of a phenomena to happen in the absence of a nucleus, which is very much true. And the reason is that the nucleus is required for the third conservation law, which is the conservation of momentum. You see, the presence of the nucleus helps in the conservation of the linear momentum of the system, because the electron and the positron are moving, right? They have some kind of a kinetic energy. There needs to be some sort of a recoil absorbed by some external particle like a nucleus. In the absence of a nucleus, this kind of a conservation of linear momentum principle does not happen, and therefore this phenomena cannot happen in empty space. The phenomena of pair production does not occur in vacuum or should not occur in vacuum. There are some exceptions, we will leave that for the time being, but it does not happen in vacuum. It requires a nucleus or some external matter particle to absorb the momentum, to balance the linear momentum conservation principle. We can show that how this is true if we assume the negative. That means if we assume that this process does happen in the absence of a nucleus, then would the conservation laws be violated? So let's check. So if I say that there is some sort of a photon that ends up creating an electron and a positron, let's suppose, let's check in the absence of a nucleus if this is possible or not. Then first of all, the scattering angle should be theta. Why? Because the electron and positron have same mass, and because they have same mass, they are going in different directions. Their momentum in the y-axis should be conserved, right? The momentum of the electron along the y-axis and the momentum of the positron along the negative y-axis, that needs to be conserved, and for that to be conserved, the angle of scattering will be equal. All right. Now the photon has energy h nu. Okay, so conservation of energy requires that h nu should be equal to the total amount of energy of the electron and the positron pair, which I have written in this particular manner. Now this is written in terms of the rest mass energy and in terms of the relativistic kinetic energies. What if I write a more simpler expression? The simpler expression will be written as twice mc square, where m is a relativistic mass, or if you're not comfortable with the idea of relativistic mass, let me write it in this particular fashion. We can also write the total amount of energy as twice gamma m naught c square, where m naught c square is the rest mass energy and gamma is the gamma factor. What is the Einstein's relativistic principle? That is E equals mc square, right? So that m could be associated with the relativistic mass of these particles. So therefore, the total amount of energy goes into the total relativistic energy of these two pair of particle system. It can be written in this manner, or it can be written in terms of rest mass energy. So I have written as rest mass energy plus kinetic energy, or it can also be written in this particular fashion. The reason being is that if you want a little bit more elaboration for any particle that has some kind of a mass m naught, which is in motion, the total amount of energy is written as gamma m naught c square. All right, where gamma is the root 1 upon root over 1 minus v square upon c square, or this can also be written as m naught c square plus the relativistic kinetic energy. Okay, so you can either write the total amount of energy of a relativistic particle as a rest mass energy plus the relativistic kinetic energy, or as gamma m naught c square, which is basically the total amount of energy of the particle. So here I have chosen the different expression. The reason will become clear in a moment. And second, if we look at the momentum, so initially here we have the energy conservation principle. Okay, this is point number 1, let's suppose. And if we look at the momentum conservation, then what is momentum? Momentum is equal to E upon C, which is equal to h nu upon C, right? So if we look at the momentum conservation along this particular axis, so let's say that this is the x-axis. So along the x-axis, what does the momentum conservation tell us? It says that the initial momentum h nu upon c is equal to the total momentum along x-axis of both the electron and the positron, which is twice p cos theta. Then we consider both the momentum of electron and positron to be equal, so we end up getting this particular expression, which is nothing but hc is equal to 2pc cos theta. But what is p here? P is momentum of a particle, right? Again, what is the momentum of a particle? The momentum of a particle is gamma m naught v. Okay, m naught v is the momentum of a particle in non-relativistic scenarios, and gamma m naught v is the relativistic momentum of a particle in relativistic scenarios. So therefore this becomes h nu is equal to 2. So if I say gamma m naught v c cos theta, this can be written as h nu is equal to 2 gamma m naught c square v upon c cos theta. Now notice the expression here. These are all constants, right? Gamma, m naught, c, etc. What is v upon c? V upon c is always a quantity that is less than 1. Always. Because you can never really go beyond the speed of light. So for any matter particle like an electron or a positron, V upon C will always less than 1. What is cos theta? Cos theta is also always less than 1 by definition of what a cos theta is. Therefore, this conservation of momentum along the x-axis tells us that h nu should be less than 2 gamma m naught c square, right? V upon C is some number less than 1. Cos theta, some number less than 1. So these two numbers which are less than 1, if I multiply it with this, so therefore h nu should be less than 2 gamma m naught c square if I remove this, right? These two quantities are less than 1. Therefore, if I remove them from the expression, h nu should be less than 2 gamma m naught c square. But this is point number 2 is not agreeing with point number 1. You see, point number 1 says that h nu is equal to 2 gamma m naught c square, but point number 2 says that h nu is less than 2 gamma m naught c square. This contradiction arises because we do not have the presence of an external nucleus here. An external nucleus is required for absorbing some of the linear momentum in the backward direction to balance these equations so as to make the phenomena happen in the first place. Because conservation of momentum and energy is violated here, it is violated, you see, you end up getting a contradiction. In the absence of a nucleus, this phenomena does not happen. So pair production does not happen in the absence of matter. It only happens in the presence of matter when an extremely high energetic photon interacts with matter particle. One last thing regarding pair production is that it is something that only happens for extremely high energetic photons. You see, we have been talking about the interaction of radiation with matter. When low energetic photon interacts with matter particle and the matter particle like an electron completely absorbs all the energy of the photon, then we may see something like photoelectric effect. If the matter particle absorbs the energy of the radiation partially, so that the photon loses some of the energy and also gets scattered, then you get Compton effect. And if the photon has extremely high energy and loses the energy completely in the creation of a electron positron, you end up getting pair production. Now all these three phenomena happen, but they happen for different energies, right? So for low energies, you see photoelectric effect. For medium to high energies, you see Compton effect. For extremely high energies, you end up seeing pair production. So photoelectric effect is dominant for low energies, Compton effect dominant for mid energies like X-rays, etc. And pair production is dominant for extremely high energies like gamma radiation, cosmic radiation. And since we're talking about pair creation, let's also talk about pair annihilation. So pair annihilation is the opposite or the inverse of this particular phenomena. When an electron and a positron meet, they end up creating two or more photons. This is pair annihilation. This is a complete opposite of pair creation. So in pair creation, a photon with sufficient energy ends up creating a particle-antiparticle pair, positron-electron pair. But here, a positron and an electron combine to create a photon. What is the difference between both these two situations? Number one, pair annihilation does not require the presence of an external nucleus, while pair creation does require the presence of external nucleus or some matter particle. Pair annihilation ends up creating two photons or more than two photons. Two photons are created because of, again, conservation of linear momentum. You see, if you have an electron and a positron that comes and boom, annihilates each other and two photons are created, these two photons will need to travel in opposite directions, right? I mean, because if only one photon is created, that one photon will always have some linear momenta in any frame of reference. So to conserve linear momenta completely, we need two photons going in opposite directions. So therefore, always two photons are created, or at least two photons are created in the process of pair annihilation. So that means when an electron and a positron come together, they may have kinetic energies, they may not have kinetic energies, but minimum one gamma photon is created, and this gamma photon will have a minimum of 0.511 mega electron volt. Right, so they are going to be extremely high energetic photons. So whenever some kind of a positron is created at it interacts with matter, it ultimately comes in the presence of an electron, it ends up creating these gamma photons. Usually what happens is that whenever electron and a positron, they come in contact with each other, they end up creating something called a positronium atom. So positronium atom is like a hydrogen atom. So in hydrogen atom you have a not positron, you have a proton and the electron is going around it. But here in this situation you have a, because they are oppositely charged, a positron, right, which is the same mass as an electron but opposite charge, and an electron, same mass as a positron but opposite charge. They create a momentary atom, and that atom is known as positronium. And the positronium atom has a lifetime of around 10 to the power minus 10 seconds. So it's a very, very small, short lifespan, and both the electron and the positron, they spiral around each other and then they vanish and they annihilate and two photons are created. Okay, so this is like a death spiral into annihilation. Alright, so these are the phenomena of pair annihilation and pair production, two very interesting phenomena in quantum mechanics, and they validate not just relativity and energy conservation, they also validate the existence of photon particles that obey energy conservation, linear momentum conservation, just like particles do. And they are also the result, the antiparticles at least, are the result of relativistic quantum mechanics proposed by Dirac later on. So that is all for today. I hope that you found the discussion interesting. I will see you in the next class. Thank you so much. Bye-bye. Take care.